Ready to go for learning oxidation reactions on alcohols. Here's the paper packet, which you hopefully have possession of, and if you don't, then it's on Blackboard. This material is taken from chapter 12. So welcome. Welcome to your lesson. Hope you get a lot out of it. So we're looking at, we've already seen substitution reactions. Where a leaving group such as a halogen leaves and an incoming group such as a sulfhydryl group SH can take its place. So we've seen elimination reactions where we will have a leaving group leave and this time form a brand new double bond. This will be our next type of reaction, oxidation reactions on alcohols. So if you remember, there are probably 8 different types of organic chemistry reactions. And so the oxidation reactions, there's a symbol for this. Feel welcome to use it. It is bracket O. Across chemistry discipline, this bracket O represents oxidation reactions. So like you saw for substitution nucleophilic, the degree of alcohol will depend upon their activity. If you remember for substitution nucleophilic, it was 1 degree and 2 degree alkyl halides, which gave a reaction, and 3 degree alcohols did not. Similarly, 1 degree and 2 degree alcohols, yes, will give oxidation reactions, and 3 degree alcohols will give no reaction. So that means we want to be able to typify an alcohol by degree. The top banner will help you do that. So to determine in the early going here, the degree of alcohol, which is the reactant on the left-hand side, circle the hydroxy group, lasso circle the hydroxy group, backtrack to the immediate carbon vertex, and we call this the carbonyl carbon atom. Doesn't the word alcohol end in OL, as does the word carbonyl? So using the word carbonyl is representative of a vertex bearing a hydroxy group, carbonyl carbon. And from there, after you find the carbonyl carbon stemming from which is bond to the hydroxyl weight, you want to count the number of carbon-carbon bonds. See if I can do a quick representation of this here. And zoom in, will you? So for a 1 degree alcohol, why is this a 1 degree alcohol? Circle the hydroxy group. Prove to me this is 1 degree. 1 degree. Circle the hydroxy group, backtrack to the carbon, and count the number of carbon-carbon bonds. There's 1. That's 1 degree alcohol, as is the one below. 2 degree alcohol, circle the hydroxy, backtrack to the carbonyl carbon atom, and you can trace or indicate somehow, as you're accustomed to, 2 carbon-carbon bonds. That's why this is a 2nd degree alcohol. And 3 degree alcohol, circle the hydroxy, backtrack to the carbonyl carbon, and again, trace or indicate 3 carbon-carbon bonds. And as such, this is a 3 degree alcohol. So hopefully you're good at classifying alcohols, because that'll be part of this business of oxidation reactions. And all things considered, a reactant with 4 carbons as you see here, will give a product of 4 carbons. So there is a consistency in carbon count. You saw that for rearrangement reactions. So speaking from my perspective, I can take a look at a student's problem and tell you if it's done correctly or incorrectly just by counting the number of carbons on the homework or the completed work. And so if I'm doing it right off the bat, you should be catching that. That way you can prevent me from deducting any points. Consistency in carbon count. Too much going on here, huh? So far, we talked about the degree of alcohol, 1 degree, 2 degree, 3 degree, and consistency in carbon count. Trying to get ready to go here. And I need to reinstall hydrogen, so please forgive me. Yeah, we're looking like that. This is a reagent I'll talk about on the next page. This is one of our oxidation reagents. You can purchase it on order. It's called, you'll want to know this, it's called PCC. In organic chemistry, there are plentiful acronyms. This is one of them, PCC, P, pyridinium, C, chlorochromate. Pyridinium chlorochromate. Structure on the next page if you're curious enough to look at that. And so for this indicated carbon, which I have peg chip, I'll make that a little more prominent. Let's take stock of the outcome of this. So this carbon has currently registering 1 bond to oxygen. And in the product, which I've drawn to the right, it will have 2 bonds to oxygen in terms of a pi bond and a sigma bond. A double bond is composed of a sigma and a pi. So you have 2 carbon oxygen bonds. You can see them there. So that's what constitutes an oxidation reagent. But carbon can only have 4 bonds, right? So if we're increasing the number of carbon oxygen bonds, if carbon's still going to have 4 bonds and be under octet rule, another type of bond has to be removed, and that is the bonds to the hydrogen atoms. This will swing from 2 to 1. And there's different ways to show this. Do you know the functional group here? It begins with the letter A. It's an aldehyde. We have just formed aldehydes, which is a type of carbonyl compound. Aldehydes, a type of carbonyl compound. A type of carbonyl compound, aldehyde. And there's more than one way to draw an aldehyde. And hopefully you can register for yourself that this does have 1 hydrogen there. And aldehydes can be drawn either way. Well, I just drew out the hydrogen, but you may run into aldehydes where this aldehydic hydrogen is not drawn out. So you can see for yourself, we have increased the number of carbon oxygen bonds from 1 to 2. Hence, this is called an oxidation reaction, not an elimination reaction, but an oxidation reaction. Next storyline, what if we used a different reagent? Can you count up the number of oxygen atoms in this formula here? This is sodium Na2 dichromate, Cr2O7, sodium dichromate. It's a solid powder, and this is sulfuric acid. This adds up to, count them, 11, that's over 10, 11 oxygen atoms in the reagent. pretty hefty, right? So we're seeing this is a more severe reagent than PCC, which I'll show you on the next page. It doesn't have 11 oxygen atoms. So we have one carbon-carbon bond standing true after the fact. We're looking at this carbon here, shipping it for you now. And we started with one carbon bond at that carbon where I'm circling over here. On the reactant on the left, we're starting with one carbon-carbon bond. Okay, I can indicate it. That's the one we're talking about. This is the one we're talking about here. One started with one, that's going to remain the same. You can take a look for yourself. This is now 3. 2 is a double, 1 is a single. Carbon-oxygen bonds. That's an oxidation, right? It went from 1, it ends at 3. We've increased the number of carbon-oxygen bonds. So this is an oxidation reaction. At the expense of removing these hydrogens here, they are in the byproduct. So they're not in the organic structure anymore. So 0. So register a 0 there, because if I look at this carbon here, this carbon, which now I will pinpoint with an arrow, that doesn't have any hydrogens, does it? No. No. It already has 4 bonds. It can't have hydrogens there. So that's an oxidation reaction. And this, by the way, is called a carboxylic acid, if you remember that. Carboxylic acid. Not an ester, but a carboxylic acid product. So we can turn an alcohol into a carboxylic acid. Then the acidity level will drop. The pKa of an alcohol is probably 15. The pKa of a carboxylic acid is 5. So in so doing, we have increased the acidity of this organic compound over 1 billion times. 10 to the 9th, 10 to the 10th, over 1 billion times. Over. So here we have a 2-degree alcohol. If you recognize this, here we have a ketone, not an aldehyde by the flow chart. Sufficient time was spent. And for the carbon-all-carbon, you have, we're talking about oxidation reactions. Standing already, we have 2 carbon-carbon bonds, one to the left, one to the right. And you can see what else this carbon is doing. This carbon-all-carbon is bond to an oxygen and a hydrogen. By the way, remember, as I talked about earlier, oxygen can make 2 bonds. That's what oxygen does. Nitrogen can make 3 bonds. I told you how to generate that and not have to memorize it back in chapter 1. So we're not talking about that. We're talking about oxygen now. So again, the number of carbon-carbon bonds at this position here, so indicated, is 2. That has not changed, but we have gone from just 1, doubling that to 2 in the form of a double bond, which is equal to a sigma plus pi, if you remember. Double bonds equal to sigma overlap and concomitant pi overlap. 2 types of overlaps. And now, how could he say there is any hydrogen there? There's not at the green indicated vertex. So still carbon has 4 bonds, 2 plus 2 is 4. So, and you have the same number of carbon atoms in the reactant and the product, 7, starting with 7 carbons overall, going 7 carbons in the product, forming a ketone in this oxidation reaction overview. Here we have a 10-carbon 3-degree alcohol. Reportedly, I can't put in a hydrogen there, else I have 5 bonds at a carbon. Oh, look at this. So you cannot. And so here's a story here for you. I'll type this out. In order to be eligible for I'll use the abbreviation, oxidation reaction, there must be at least 1 carbonyl, that's the chip for the circle hydroxyl backtrack to carbon. That's the carbonyl, 1 carbonyl carbon hydrogen bond. That's textbook explanation. In order for, that's why 3-degree alcohols cannot undergo oxidation reaction, because if we're going to supply yet another bond to oxygen from carbon, we have to remove something. Otherwise, we'll be above 4 bonds to carbon. So we remove carbonyl hydrogen and increase carbon oxygen. Can't do that if there's not a carbon hydrogen bond. no reaction. So 3-degree alcohols, it's easy points if you know it. 3-degree alcohols give no reaction for oxidation. Just like you saw, SN2 reactions give no product for 3-degree alkyl halides. They give no product. So just it's similar enough to SN2 business, where 1-degree and 2-degree reacted, and 3-degree did not. I will add that 1-degree reacted quicker than 2-degree back in SN2. To that extent, that's the same here, where 1-degree alcohols are more reactive than 2-degree. They'll both react, 3-degree will not. Taking a look at some of our reagents here. This is called pyridinium chlorochromate, PCC. You can order this on aldrich.com, but be careful. You ever seen the movie Aaron Brockovich? It's a movie about an environmentally conscious employee who crusades against chromium poisoning of the waters. Aaron Brockovich, as played by Julia Roberts. And this is why we don't do this lab on the premises. Oh, that's why, because it would be big fine, trouble, wreak environmental damage if chromium was to escape into the sink down the drain out the building of opaque science hall. That would be very bad news. That's why we don't use chromium on the premises for 200 level laboratories. Back to business. This is a milder oxidizing reagent because there's only 3 oxygen atoms in the structure. Also, pyridine here, which is a nitrogenous aromatic ring, is hazardous to reproductive systems. So that's also a reason why we don't want to use this reagent in anywhere near a 200 level laboratory. But even so, this is a 3, it's a milder oxidizing reagent because of the number of oxygen atoms it has. So I need you to know, I don't need you to know how to draw the structure of PCC, but I do need you to know that PCC, I always look at the acronym, PCC, 3 letters, right? 3 oxygen atoms. Great. Now, class, you will need to draw this formula correctly. I've said before, 22724, you're going to need to remember the subscripts. Na2Cr2O7 H2SO4. It has to be that, okay? You have to communicate what reagent you need. So I will need you to, while I don't need you to draw the structure, I do need you to know the subscripts. I'll do them live for you. 22724. And you should do this too. The more times you write it out, the more you'll remember it. And you can see that, as I have mentioned, this will add up to how many? 11, which is more than 3, 11 oxygen atoms. This is a more severe or stronger oxidizing reagent. There's different strengths of reagents, class. PCC is a weaker, more milder reagent. Sodium dichromate sulfuric acid, Na2Cr2O7 H2SO4, is a more severe reagent, because I will type here it has 11 oxygen atoms in the combined structures in the combined reagents. So back in general chemistry, perhaps you saw that if you take copper 1+, pull off an oxidation reaction to copper 2+, that was what's constituting an increase in charge. So that's an example. Copper 1 plus oxidized to copper 2 plus. You'd see because it would go from a tea-colored appearance to an aquamarine appearance, copper 1, copper 2, respectively. As I said before, as the number of carbon-oxygen bonds increases, the species becomes more oxidized at the expense of reducing the number of carbon-hydrogen bonds because carbon can only make 4 bonds. And I will choose not to review this in depth, but I will say that when you're doing oxidation reduction reactions, you will have one oxidized species on the left, and that species becomes more reduced on the right. So maybe in this instance, we're going from chromium 6 to chromium 3 plus. So we're reducing in charge. And for instance, for our reactant on the left, it's more reduced form. So maybe this compound has only one carbon oxygen bond in the form of an alcohol. And in the product, maybe you made a ketone because it's a secondary alcohol. So therefore you have 2 carbon oxygen bonds. So whenever you have oxidation, you have to have reduction, whether it's reduction in charge or reduction in the number of bonds. So take a look down here. Manganese 4 plus is getting oxidized to manganese 7 plus. That means that the charge is increasing. And here we have 3 carbon oxygen bonds going to 1 carbon oxygen bond. So long and short of it is, when you have an oxidation, you will have a reduction concomitant. Where there is an oxidation, there has to be a reduction. Otherwise, you have an unbalanced equation. So this is our key. Zoom out at the key. So let's consider this key is set up where there are 2 factors at work. The first factor, and maybe you've heard of it, is the degree of alcohol. Factor 1, degree of alcohol. Either it's 1 degree, 2 degree, or 3 degree. The second factor is the strength of the reagent, whether it's a strong or a weak reagent. Strong reagent, sodium dichromate, sulfuric acid, Na2Cr2O7 H2SO4, 22724. And the weak reagent is PCC. How many oxygens did that have? You remember? 3. PCC, 3 oxygen atoms. So let's inspect our key. As I said, there are 2 factors at work. There are 2 factors at work in this key. Factor 1, degree of alcohol. 3-degree alcohols will not oxidize. Factor 2, strength of oxidation reagent or oxidizing reagent. Is it PCC or Na2Cr2O7 H2SO4? PCC or sodium dichromate sulfuric acid. Those are the 2 factors at work. So here's our key. In PCC, I call it the world famous one-step reagent. So PCC will increase the hashtag number of carbon oxygen bonds by a unit of 1. PCC, the one-step reagent, increases the number of carbon oxygen bonds by 1. PCC is the world famous one-step reagent. Increases the number of carbon oxygen bonds by 1. Whereas sodium dichromate as you remember, is the more severe reagent. So this will have the capability, sodium dichromate sulfuric acid will replace all carbon hydrogen bonds at the carbonyl carbon atom with carbon oxygen bonds. So like we saw over here, here are the two hydrogens at the carbonyl carbon. They are both going to be replaced. They're both going to be moved away. They're not there anymore. I did have one carbon oxygen bond and two carbon hydrogen bonds. And now if I presto turn the two carbon hydrogen bonds into three carbon oxygen bonds, that's the outcome. That's what sodium dichromate sulfuric acid has a capability to do. It will replace every single one of them, carbon hydrogen bonds with carbon oxygen bonds. When it comes to secondary alcohols, and we'll have a worksheet about this, there's only one carbonyl carbon hydrogen bond. Therefore, you can only oxidize once. There's one carbon hydrogen bond. We had one carbon oxygen bond originally. If you presto turn the one carbon hydrogen bond into a carbon oxygen bond, you end up with two. And PCC is going to give the same product because PCC is the world famous one-step reagent. So you're going to start with one and with two. So as happenstance would have it, you have the same product, whether or not you use whatever strength of reagent for second degree alcohols. For 3-degree alcohols, there's going to be no reaction, as previously stated. So the thought and the carefulness has to be there in some of the worksheets. So you don't, what we don't want to do is don't break the octet rule. We you have to have carbon with 4 bonds. You have to have neutral products. Do you see any charges on these products to the right? Nope. Neutral products. No metal products. Do you see any organic products with any chromium in them? Nope. No metals in organic products. So we don't want that. You have to have carbon count conservation. If you start with 6 carbon atoms, you should end with 6 carbon atoms. So these are the things we're thinking as we start to concern ourselves with practical natures of these matters. A nice enough key. Some mechanistic concerns are valued here, but these problems that we're going to be doing will not be solved with curly arrows. So we're electing to understand that the reaction will commence through the conduit of curly arrows, but for our problems and our derivations, our answers, we will not have any curly arrows in any answers. Well, here's a homework page I inserted in here, so maybe explain this the mechanism a bit. So the mechanism does deserve some explanation, but I'm not going to focus on it. So here's a nice question to ask yourself. Is this alcohol here primary, secondary, or tertiary? 1 degree, 2 degree, or 3 degree? Take a few seconds to think about that. Okay. Circle the hydroxy, backtrack to the carbon, and trace the number of carbon-carbon bonds only. I see there are 2. This is a 2nd degree alcohol. This, by the way, is isopropyl alcohol, available at any Walmart. And here we have acetone, again, available at any Walmart. We're forming a ketone, 2nd degree alcohol. I hope you got that right. So what mechanistically curly arrow-wise happens is you'll get deprotonation. So doing this yields that. And then an application to follow in March or April is you box water. If I box water here, isn't in the box it's HHO or H2O, right? So this is a condensation product, almost like how dew condenses on the grass and the cold dawn morning. So HHO, H2O, there it is. There's the HA label for you, the acidic hydrogen. Now we have what's called a chromium ester, and we're doing reactions in water. So this is the carbonyl carbon hydrogen bond here. Carbonyl carbon hydrogen bond. There's one of them. One is present. This bond is removed and replaced by a new carbon oxygen bond. The electrons in the new carbon oxygen pi bond were originally held by the carbon hydrogen bond. That's where the electrons originated from. Please make a note of it. And that would yield up the answer up above. So I know you can interpret curly arrows. Let's move on. Some new challenges. Now, here are challenges. One of our challenges, here's how these problems will be arranged for you guys. So one of the challenges will be if you're given the alcohol and you're given the reactant structure, line angle formula, chem draw on the left, and you're given the chem draw structure on the right, what reagent, PCC or Na2Cr2O7 H2SO4, what one was it? One or the other caused this reaction to occur. So there's that problem. And remember, PCC is the one-step reagent. So I'll come back to that. Another problem, which is very common, is you're given the chem draw structure on the left, and you're given the particular oxidizing reagent, PCC or sodium dichromate sulfuric acid 22724. One of those. So you're given the chem draw structure of the alcohol, and you're given the formula of the oxidizing reagent, and you're asked to draw the product forward. What is the product structure on the right? And finally, which takes some thought, is you may be given the product structure on the right and the identity of the oxidizing reagent, and then you're asked to come up with the identity of the alcohol. And remember that alcohols still only have one carbon oxygen bond. So this worksheet ahead will help us with that. And now just a bunch of worksheets and application. I will not do all the problems, but I will do a representative amount. An instructive amount. All right, so thank you for continuing to tune in. I hope you're following. I believe I'm doing a very clear job at presenting this, not missing any angles. So what is it? What is the reagent here? We're looking for this. Which one is it? So we start with how to solve that is you have one carbon oxygen bond to the left, and I account for 3, don't you? Carbon oxygen bonds to the right. You have a double and a single adding up to 3. So how can this be PCC? If PCC is the one-step reagent, it can't. This is the stronger oxidant. Wouldn't a stronger oxidant increase the number of carbon oxygen bonds more pronounced in a more pronounced type of way? Slash, please. And likewise, so hopefully these are not that hard to solve, I would hope. On the product side, here's 2. So therefore, this is, as I said, the world famous PCC, the one-step reagent, pyridinium chlorochromate. If you're interested in how PCC can halt that reaction at the aldehyde, then please see me. I can explain it to you. But it's beyond the scope of this video. And then we're going to try this PCC one-step reagent. This is a 1 degree alcohol. So let's see, let's recopy the structure to the right. Let's take the advice sheet I printed up for you. Sorry, it's not maybe formatted the most stunningly, but it's still serviceable. So recopied it to the right. Please bear with me. Now we're going to edit our structure. So PCC is the one-step reagent. One step, that means we're going to increase the number of carbon oxygen bonds by 1. Oh, I guess it did that for me. So I'm going to do parallel-wise to answer to that. As I remember, oxygen can only make 2 bonds, can't it? That means I have to erase. I don't think I'm going to have such luck here, but I'm going to do this. I have to erase the hydrogen. You'll see what I do. Please again, bear with me. So, thank you. I have to erase the hydrogen. That way oxygen has 2 bonds. Don't be too impressed. I'm not that smart. And we're done, actually. That's it. I do have the same number of carbons before and after. Like a big scribble over here. That way I know where it is. And let's look at the next one. All right, so let's copy out the next one. Look at this. We're drawing the product if given the alcohol and the stronger oxidizing reagent. This should be interesting, don't you think? I could do this a lot faster. I was working on the marker board, so sorry. Let's see, I want to, what's the next thing to do? Okay, input additional carbon oxygen bonds according to the oxidizing reagent. Do you remember the maximum number of carbon oxygen bonds was 3? You remember that in the previous handouts? Otherwise, you can harken back to the number of carbon hydrogen bonds. So I'm going to brace this here. You know what? We can take a look at, isn't this carbon? My hands are off the mouse and the keyboard. Isn't that carbon the one which is bonded to oxygen? Right now I have how many quantity carbon oxygen bonds at that red chip? 1. Let's turn it into 3 quickwise, shall we? This is the easiest way to do it. Done. Turn it into a carbonyl and you're done. Same number of carbons, 5 carbons before the change, 5 carbons after the change. Good for checking that out. Looking at 1 degree alcohols, you can see one yields an aldehyde and one yields a carboxylic acid. And here, let's think alcohols, okay? Which alcohol has this same backbone, same branching, same number of carbon atoms, but only 1 carbon oxygen bond, where recall oxygen makes overall 2 bonds. Well, it says that up above, but these are alcohol. We're looking for alcohol reagents, everybody. So I'm going to do the bottom one first, if I may, with the PCC. Oops, so we'll try again. I recopied it to the left. Now you can work faster if you like, but I'm just taking it step by step. I recopied it to the left. The very same, isn't it? PCC, what do you know about that? It's the world famous one-step reagent. It takes whatever you have and increases the number of carbon oxygen bonds by 1. This is 2 carbon oxygen bonds, therefore, and I have to adopt this so this now has 1 carbon oxygen bond. That's the challenge. The challenge is there. How can you rewrite that structure that it has 1 carbon oxygen bond? And then edit for octet rule. I'm now changing to something, an eraser of a kind, and erasing one of these bonds. Getting there, getting there, getting there. And then, if you will, remember the oxygen has 2 bonds. And we'll have to reinstall that. Ooh, I'm trying to get a hydrogen in there. Okay, so trying to convince this computer to help me write a hydrogen there. How about green? Yeah, wait, still. Ooh, okay, all right, let's try hydrogen. Because oxygen needs 2 bonds, right? You can either draw the bond out or collapse it. It's up to you. Whatever your preference is. Okay. I will cover this on the next page because it's getting kind of crowded here. I only have that much room. So let's move on. Onward. Rotate the view. Okay, great. Now here's some more practice for you. So PCC is the one-step reagent. So we're given the chem-draw structure of the alcohol and asked to write the resulting structure of a carbonyl. I'm going to recopy the structure to the right. I'm going to have to edit it for octet rule. PCC is a one-step reagent. Isn't this carbon the one which is bonded to it? Make that a double bond. Almost, guys, almost. Now, I just have to edit for octet rule. I was going to try something, but it looks like it's not cooperating. So, ooh, I think we may have it there. Get this box to move up here. Almost. You should end up with a carbonyl. You see, class, every product you're going to be drawing in this arena of chapter 12 will be carbonyl C double bond O on the right side. Has to be. Take a look over here. Check, 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 check. Each one of them has a C double bond O. Giveaway, giveaway. So this is a 1 degree alcohol. What type of alcohol will we have here? 1 degree, 2 degree, or 3 degree? 3 degree? You say that? If so, well, are you impressed? 7, 4, 11 oxygens. Whoa. Wow. Are you impressed? Well, the 3rd degree alcohol isn't. So therefore, no reaction. No reaction. It will be a red letter day. It would make the 6:30 news if chemists could find a way to oxidize 3-degree alcohols. Hasn't been done yet. I don't think it's ever going to be done, but never say never, but never. So, and next one, we have a 1-degree alcohol. Well, this will keep us on our toes here. Recopy that, will you? Same number of carbons, same branching. Don't want to make a mistake. Don't want to skip a carbon or have too many. This is the carbon of interest bonded to the oxygen. That's the only, if you take a look at that global molecule, that's the only carbon which is bonded to oxygen. We're thinking there. 1-degree alcohol. This is the super oxidizer. This is not the one step. It goes to 3 carbon oxygen bonds. How can we do that? See that peg chip? Add a carbonyl. And you're already there. Octet rule is perfect. Here's the super oxidizer. What type of alcohol is this? 2-degree. And so, where there's a wedge, there's a hash, and vice versa. 2-degree alcohol. If you remember that 2-degree alcohols give the same product for whether it's PCC or Na2Cr2O7 H2SO4. If you're not sure, try it. Maybe you're thinking this should be a carboxylic acid. I can ram up against that boundary, put that there like it used to be. Okay, force it. Go ahead. I dare you. Make it a carbonyl. And you will see that this is octet rule violated. Do you? Can't have that. That's nonsense. So you will erase that if you please. And instead, we will brace parallel-wise a brand new bond to oxygen. And you guessed it, oxygen has only 2 bonds. And so therefore, I have to somehow, if the computer permits, erase the hydrogen. Will it? Oh, almost. And you're done already. Okay. And you remember how we do these, right? We recopied over here. This time it's even more difficult because the reagent is not given. So I'm going to do every other one because, I'm going to do H because we need to do H. E and H will be representative. For H, do you see? Oh, say, do you see that this has 3 carbon oxygen bonds? Everything on the left-hand side that we're going to be drawing as final answer should have only 1 carbon oxygen bond. Take a look. Take a look. Take a look. Every reactant we want to draw over here will have 1 carbon oxygen bond. How can that be engineered? How can we turn this into 1 carbon oxygen bond? Remember that oxygen makes 2 bonds. Oxygen makes 2 bonds. And as such, we're going to need this tool here. So scribble, 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 scribble. I'm going to edit it to change the number of carbon oxygen bonds from 2 to 1. It doesn't matter which one you would erase, as you probably know. Ooh, get in there. Goes in there like that. All right, we're looking better. Partial credit has been afforded, has been paid out just right now. So the ATM machine has paid out some partial credit for that. But in order to get the full credit, you will be asked to copy out and reflect the oxygen as 2 bonds, and we're going to make that the hydrogen after water workup. Edit red. Okay. Ooh, please, red. Okay, got it. Trying to get in here. H. OH. A better way to do that. Kind of hemmed in by the oval, but it wasn't there like that. It's an alcohol, right? Weren't these alcohol? Wasn't this an alcohol? We're making alcohols. A one-step reagent, right? Goes from 1 carbon oxygen bond to 2 carbon oxygen bonds. So that's the one-step reagent, that's PCC. To 2 carbon oxygen bonds. Down here, again, I need 1 carbon oxygen bond. This on the left, and this turned out to give 3 carbon oxygen bonds on the right. So I'm thinking I'm going to type here the super reagent, sodium dichromate 227 sulfuric acid 24 H2SO4. Hope you wear gloves for that. Eraser. What do you think my chances are? I want to erase the carbonyl. That should take me to where I want to go. Not too bad, eh? Worked pretty well, electronically speaking, and chemically speaking too. And we're done. And I hope you know that this one here, take a look, you have 1 carbon oxygen bond, 3 carbon oxygen bonds. That can't be PCC, can it? How could it? This is 1 carbon oxygen bond. PCC is the world famous one-step reagent. The 2 carbon oxygen bonds. This is PCC, no doubt. Without a shadow of a doubt, that's PCC. This is, if you can remember the 22724, how many times have you written that so far? The more times you write it, the more times you remember it. There. And the next page, rotate the view. Okay, where is it? We're going to have 1 degree, 1 2 degree, and 1 3 degree alcohol. I want to find the 3 degree alcohol because I know it's going to be no reaction. Let's find out. Where is it? Which one of these is a 3 degree alcohol? I'll let you think. Which one is a 3 degree alcohol? The one in the middle, you said? Correct. This is a 3 degree alcohol. Happily, I will put nothing changed. Nothing changed. When a police officer would pull someone over for drunken driving, that officer, he or she in their trunk has a breathalyzer test. And so someone with alcohol on their breath, you could smell it. You can smell when alcohol is on someone's breath. They would blow into the breathalyzer, and in the trunk of the police car is a spectrophotometer, and this can detect a change in appearance for the chromate agent. It's the more green it is, the more alcohol there is on someone's breath. Different breathalyzers. You can see here, someone should not drive. Here, see the big Ghostbusters mark on the car there. See how green this turned? That turned pretty green. That's someone drank a lot of alcohol in their breath and their blood above the legal limit. And let's see, breath test to measure blood alcohol level. So this white stuff is silica gel. I just read there. So yeah. You think you did a column on that, didn't you? And see changing color UV vis spectrophotometer in the trunk of the police car. Neat. Good stuff. In our bodies, we don't have class. We don't have PCC in our cartilage or our muscles or the nervous tissue or endocrine system. We don't have any of that PCC or sodium chromate sulfuric acid. No, not at all. We do have nicotinamide adenine dinucleotide, oxidized form, NAD plus, nicotinamide N, adenine A, dinucleotide D plus, the charge on that. And we also have flavin, adenine dinucleotide, FAD. You'll see these on some cereal. If you look on the box of a cereal, box of cereal, turn it, skinny panel. You ever see niacin, flavin? This is oxidation agents your body needs to get energy from food. Niacin and flavin. So you can see the chemical changes that NAD plus undergoes. Oxidized forms on the left, reduced forms on the right. You can see there's an extra hydrogen there, isn't there? I count 4 red and 5 blue, so more hydrogen. So that's how your body will pull off oxidations of alcohols. Sometimes people who drink alcohol, they develop acetaldehyde in their blood. That's the liver detoxification product is acetaldehyde, an aldehyde of 2 carbons. And here's flavin, adenine dinucleotide. And in the red, I don't see any hydrogens. In the blue, I see 2 hydrogens. That's why it's called FADH2. Biochemistry related. So I hope in that spiel you didn't forget what you're supposed to do here, right? So, zooming in here, this is a 1 degree agent, all shuffled up, but nevertheless, this is a 1 degree. So we're going to recopy this. I think appropriate answers and solutions were given above. So I'm just going to go directly to the answers. That's for PCC, the 1 separation. I hope that's predictable. What would the answer be for the super agent? I'll wait 20 seconds. Okay, here goes. I want to go from 1 to 3 carbon oxygen bonds. That can be done if you add a carbonyl C double bond O at the correct carbon atom, which is here. Because this carbon is already bonded to an oxygen, is it not? So I click connected a carbonyl. Chemically speaking, that happens through curly arrows. We handle 1 degree. There's a difference in products there, isn't there? But each product has a carbonyl, does it not? C double bond O. Here's 2 degree. If you remember your key, the same product will occur for 2 degree alcohol. So I'm just going to draw it once. Double bonds are flat, don't you know? So that means I'm going to get rid of the wedge there. That's for both. Make this look a little nicer here, if I can. Trying to make this a nice looking hash. And I need it to be ethyl anyway, so. It's the same, reasons discussed above. Editing for octet rule, make sure your number of carbons are the same. No metals in products. Make sure you don't break the octet rule. And the next one. Let's look over here. Where can I enter in PCC? Can I enter it in above or below? Or are we increasing the number of carbon oxygen bonds? Going this direction or going that direction? Increasing, getting higher in a number, quantity of carbon oxygen bonds. I suggest to you it's here. I would suggest. And what's the opposite of PCC? We have not covered that yet. We will. That's going to be a lab you'll do on vanillin. That's called sodium Na boro B hydride H4. Less harmful than chromium reagents for sure. You'll be using that there for. And what else? Water workup. Water workup. That's the cycle. So PCC is counteracted by sodium borohydride, H2O. I'll type this for you, maybe in case I would need to do that. 1 NaBH4, which means that you add sodium borohydride powder, sprinkle, stir, heat. Then 40 minutes later, add water to water. Okay, that's that. So you're responsible for that. What counteracts PCC is sodium borohydride. And I will now add, this is an oxidation reaction, O bracket, and the opposite of that is a reduction reaction, RR bracket. You're reducing the number of carbon oxygen bonds from 2 to 1. This has 1, in case you need to know, carbon oxygen bond. Here we have 2 carbon oxygen bonds. To change an OH into a Br, it's kind of unrelated to oxidation, but we should have a reagent rich in bromine. Here's one, phosphorus P tribromide. That will do it. Works for 1 degree and 2 degree alcohols. For 3 degree alcohols, you need a different reagent. I will keep that secret for now. And what happens, this is going to be an SN2 reaction here, and that's going to be brought forth by sodium hydroxide, where sodium Na plus is a spectator ion. Hydroxide can smack a backside attack. It can snap like that. Bromine has the requisite usual number of lone pairs on it, and that can bring about. So that's good to know. How to interconvert an alkyl halide and an alcohol OH. What else is on this packet of fun? You've seen that before, haven't you? PCC 1. Remember? NaBH4, sodium borohydride. Mechanism to be discussed. For sodium borohydride, we will cover curly arrows for that. You see, class, we use curly arrows when they're streamlined and useful for us to solve problems. I don't want to have to solve oxidation reaction problems, having to do curly arrows each time. I would rather not. I would rather not have to do that. See, I'd rather not have to show these curly arrows each time I want to solve a problem. So we make choices here and there which are intelligent when and when not to use curly arrows. And this is a choice where we're not doing that. We're not using curly arrows. How about this one? OH to Br. I probably need a lot of bromines, right? You remember it? PBr3. How do you replace a bromine with an OH? NaOH. Why don't they make up their mind? Don't blame me. Hey, these are the same compound, right? So who's playing games with us? Feel like a fool. And we had it like this and told me to put a bromine. Now you have an OH there. So what do you want? And here we have 1 carbon oxygen bond to 3 carbon oxygen bonds. What do you think that could be? Ooh, it's not the one-step reagent, is it? So it's going to be 22724. How can I supply Let's go through this one. How can I supply an additional H and an additional plus onto an alcohol? How about acid? Can an acid or it be written H plus Cl minus? H plus. Oxygen has how many lone pairs? The same as it has bonds, 2. Oh, they're there. Isn't that nice? By now, you can write HCl as H plus Cl minus. From these dots, electrons. Electrons are negatively charged. Why would a negative charge attract to a negative charge? Probably not. So, spectator, that's how you get that. And this is going to be NaOH up here. Type that in there. It's a chapter 2 reaction. Chapter 2, Bronsted-Lowry. Na plus spectator and a negative charge, OH. That's where the negative charge comes from. And you get a byproduct of water. So that's our map. Mapped out like that, derived like that, logicked out by that. And now you know something about oxidation reaction. That's your third type of reaction for organic chemistry. The fourth type of reaction will likely be reduction or nucleophilic addition to a carbonyl. Okay, signing off, and thank you.